Okay, welcome back to the ChemDoctor. This is in this video we're going to deal with Le Chatelier's principle, which has to do with chemical reactions that are at equilibrium, and then the reaction is altered in some way to push it away from its equilibrium position, and then the issue is which direction does the reaction shift in order to reattain equilibrium. And there are three ways that you can alter a chemical reaction's equilibrium position. You can do it by manipulating the concentration of the components that are in the balanced chemical equation. You can do it by altering the pressure of the gas species by manipulating the volume of the reaction container, and you can alter the temperature. Now, I have talked before about the fact that equilibrium constants are dependent on temperature, and we're going to get into a little bit more detail on that now. So if we consider this reaction, the reaction of C2H4 in the gas form plus Cl2 to produce C2H4Cl2, this is an exothermic reaction, which means that energy is released over the course of this reaction. If you were to hold this reaction vessel in your hands as the reaction took place, more than likely you would feel the reaction vessel warm up in your hands. If there's enough energy released, it may even become hot in terms of your perception. If we draw an energy diagram that reflects this reaction this way, so we have our graph, and on the horizontal we just have reaction progress. On the vertical axis we would write delta H if we're at constant pressure, and the reaction diagram for this particular chemical reaction might look like this, where we have our reactant starting out arbitrarily somewhere located here, and then the product platform is going to be at a lower position. So I'm going to mark this as reactants, and this is the products. And this position here would be, might call this H1, and this position here would be H2, and the difference, energy difference, is going to be the delta H, which in this case is going to be associated with a negative sign, because the negative sign indicates that energy is being released in this reaction, which is the hallmark of an exothermic reaction. So I can rewrite this equation, and what I'm going to do is rewrite it to show the energy produced as a product, because it's being produced as a function of this reaction. The other thing about this is that, the viewer may realize this if you've already had this section on thermodynamics, but the other thing about this is that the energy released is produced. This is produced as a function of the balanced equation. So, in other words, the amount of energy produced is dependent on how much material is being funneled through the reaction. So if we were to use, say, 1 gram of the starting material here and pump it through this reaction, the amount of delta H produced, the amount of energy released in the reaction, is going to be directly proportional to the amount of material that was actually utilized to run the reaction. So you can consider the energy released to be a product of this reaction. So in terms of Le Chatelier's principle, if we had a way of removing this material, so if we could extract this material over the course of the reaction while the reaction is running, then we could fool this reaction into thinking that it has not reached equilibrium, and the reaction will continue to shift to the right. So for an exothermic reaction, if we cool the reaction, so if we cool the reaction will continue to shift right. Right, the reaction will continue to shift to the right. So for exothermic reactions, where you want to increase the amount of products that are being produced, you want to cool the reaction. So for exothermic reactions are cooled in order to shift towards more products. So the other side of this coin is that for an exothermic reaction, you definitely don't want to heat it, because that's the same kind of idea as we've talked about in previous videos that dealt with Le Chatelier's principle. If we were to heat this reaction, that would be almost the same difference as adding product to this reaction, which would cause the reaction to shift actually to the left. So if we want to produce more product, and I'll underline this just to emphasize that fact, then what you want to do is actually cool the reaction. And that has the effect of literally removing the energy into the surroundings as the reaction proceeds, and it actually has the effect of tricking this reaction into a situation where it is unable to attain equilibrium, and so the reaction just keeps funneling to the right. It keeps producing more of the C2H4Cl2. And with that, I'm going to go ahead and close this video.